Okay, so combinations, or how many ways are there to pick k out of n elements when the order does not matter? Okay, so we know already how to pick 3 out of 7 elements when the order does matter, right? So what we have is that we have 7 choices, 7 choices for the first, 6 choices for the second, and 5 choices for the third. And what we get is therefore 7 times 6 times 5, which can also be written as 7 factorial divided by 4 factorial. Okay. But the point is that now we're not interested in the order. So for us, if this is the order is 3, 5, 4, it's not any different if it is 3, 4, 5 or 4, 3, 5 and so on. So what happens is that when we count with the order mattering, we're overcounting. We're counting several times the same choice of a subset of size 3. Okay, and how many times exactly? Well, we already know that. It's the number of ways to order 3 different elements. So that is 3 factorial. So what we need to do is take this number and divide it by 3 factorial. And now we have this is the final result. Okay, so in more generality, the combinatorial function tells us what is the number of possible ways to choose k out of n objects when the order does not matter. And the number is c n k, that's one way of writing it. A different way is n above k, or n choose k. It's also equal to p n k, the number of permutations, divided by k factorial, or the closed formula for it is simply n factorial divided by k factorial times n minus k factorial. And this is called n choose k. Okay, so that is going to be quite useful in future classes. So let me give you another way of thinking about it, which might help your intuition. So here is another way of asking, how many ways are there to pick 3 out of 7 things to when the order doesn't matter? So what we're asking here is, how many ways are there to put 3 red balls into 7 bins, and in the complementary ones we will put blue. Okay, so this is another way of asking essentially the same question, and in order to answer it, we will start by making the balls different from each other. Okay, so and then we will place the different balls, and then we will again make an argument about overcounting. So we're going to reveal that under every one of the balls there is another ball that actually is different, has a different number on it. Okay, so now we have 7 balls that we need to put into 7 things, and that is quite well known that it is, we already know that this is 7 factorial. Okay, so so we basically put something in the first bin, 7 possibilities, 6 possibilities, 5 possibilities, 4 possibilities, 3 possibilities, 2 possibilities, and 1 possibility. Okay? But now we want to say, actually, these numbers that we put, they are not significant. Really, we have these balls to cover the ones, and the order within each color doesn't really matter. Right? So again, when we cover this, it doesn't matter if it's 1, 3 or 3, 1. So what that means is, again, that we're overcounting. So the number of ways to order the red balls is 3 factorial. The number of ways to order the 4 blue balls is 4 factorial. So what we get at the end is 7 factorial, that's when the balls are all different, divided by 3 factorial times 4 factorial. Okay, hope that helps you.